In this video, I'm going to talk about LoRA, low rank adaptation. First of all, let's talk about fine-tuning. Updating all the parameters of a model has a large potential of increasing its performance, but comes with several disadvantages. It is costly to train, has low training times, and requires significant storage. So to resolve these issues, the parameter-efficient fine-tuning has been produced. For example, we will talk about LoRA, which is the rank hypothesis that suggests we can capture significant changes that occur in a neural network using a lower dimensional representation. In the case of fine-tuning, the model weights after fine-tuning can be defined in this way. W prime equals W plus delta W, where delta W represents the update of the weights during fine-tuning. For the rank hypothesis, not all of these elements of delta W are important, and instead we can represent it as the product of two matrices with small dimensions, A and B. So the model weights remain frozen, but we just need to train these two matrices. A matrix contains a lot of redundant information. A matrix can be reduced into a set of linearly independent vectors. The number of linearly independent vectors needed to define a matrix is called a rank. The idea is to find two matrices that have a smaller rank than the original one, and that multiplied with each other give us the same matrix update weights as if we had done fine-tuning. The process is called LoRA, low rank adaptation. Recall that the weight matrices of an LLM have a lot of linear dependence, meaning that there is a lot of redundant information. This figure compares the classical fine-tuning versus the LoRA. As you can see here, this is the input X, and we end up with the output with the weight multiplied with the X. This is the classical fine-tuning. What we are going to do, we have input X, but instead of all the weight of the model, we will have a smaller weights, which represents with these two matrices, A and B, and we just add it to the frozen weight. This is the frozen weight, and we multiply it by the input X. So all in all, LoRA is a pivot, as I mentioned, a technique that only requires updating a small set of parameters. It creates a small subset of the base model to fine-tune instead of adding layers to the model. When we add layers, we call this adapters. We don't do that in LoRA. This subset allows for much quicker fine-tuning since we only need to update a small part of the base model. So in LoRA, we keep the original weights of the large language model frozen. Then we create two matrices, A and B, that when multiplied together will have the same dimensions as the model's weight matrix, which is W. During fine-tuning, we pass the input X for the frozen model and the change matrix, the product A and B, and then get the output. With this output, we calculate the loss. And using this loss, we update the matrices A and B using the classical backpropagation. And there is a video on my YouTube channel. I explained the backpropagation algorithm. We continue this process until we are satisfied with the result. In this figure, you can see here the different ranked matrices to obtain the change weight matrix. This is with rank 1, A and B, to obtain the change matrix. In LoRa, we have a hyperparameter R describing the depth of the A and B. The greater R value, the greater the amount of information these matrices have. But remember that we will have a greater number of parameters, thus computational cost will be higher. The results show that even low rank matrices perform quite well. So why do we use LoRa? What are the advantages? As a summary, it is efficient in training. In inference, it does not increase the computational cost. And LoRa will not alter the original capabilities of the model. It just reduces the memory cost associated with saving checkpoints during fine-tuning. And finally, we can create different change matrices for different applications and domains. One thing before I show you an example using the code, compressing the model for more efficient training. We can make LoRa even more efficient by reducing the memory requirements of the model's original weights before projecting them into smaller matrices. The weight of an LLM are numeric values with a given precision, which can be expressed by the number of bits like float 64 or float 32. As you can see in this figure, pi, the pi number, represents with float 32 bits. And when we use float 16 bits, how can we represent it? Of course, it will get a less accurate result. However, it's a trade-off. Sometimes we need to do that just to have the more important information that leads to better outcomes, regardless the accuracy. And we call this quantization. In quantization, we aim to lower the number of bits while still accurately representing the original weight values. So this is the pi using the float 16 bit, 3.141, and this is when we use high precision with float 32 bit. Now let's have an example. Let's put the knowledge into practice. We will fine-tune a completely open source and smaller version of Llama called Tiny Llama to follow instructions using the Q-LoRa procedure. Q for quantization and LoRa for low-rank adaptation. Consider this model a base or pre-trained model, which has lots of weights. Now, first step, templating instruction data. To have the LLM follow instructions, we will need to prepare instruction data that follows a chat template. This figure shows this chat template, which differentiates between what the LLM has generated and what the user has generated. This is the dependency, and for sure you need to use the GPU here, available on Google Colab, by clicking here and then change runtime, and you can choose T4 GPU, which is free. Then data processing. We chose this chat template to use in this example since the chat version of Tiny Llama uses the same format. The data that we are using is a small subset of UltraChat dataset. This dataset is a filtered version of the original UltraChat dataset that contains about 200,000 conversations between a user and an LLM. And then we create a function format prompt to make sure that the conversations follow this template. And we select a subset of 3,000 documents to reduce the training time. But you can play with this number to get more accurate results. And you can see one of these prompts by using the text column and with a number. to explore these formatted prompts. The step of model quantization, we have our data now, and we can start loading in our model. This is where we apply the Q in LoRA. And we use the the bits and bytes package to compress the pre-trained model to be a 4-bit representation. This is the code of the quantization. And here we are loading the train onto the GPU. Here we are loading the tokenizer of Llama. This quantization procedure allows us to decrease the size of the original model while retraining most of the original weight's precision. Now let's see how we configure LoRA. We will define the configuration using BEFT, which a library represents hyperparameters of the fine-tuning process. For example, here, the R, which is the rank, it's 64. The higher, that means you have more information, but the computation resources will be higher as well. The cost is higher. And then the training configuration. So the number of epochs, here the number of epochs and the learning rate and the LR schedule type. This hyperparameter, you can change it until you have the best and the better results. Then the training step, we use trainer.train to start the train step. And here you can have a break until it's finished. And then the merge weights. After we have trained our LoRA weights, we still need to combine them with the original weights to use them. We reload the model in 16 bits instead of quantized 4 bits to merge the weights. Although the tokenizer was not updated during training, we save it to the same folder as the model for easier access. And if you use the same, you can find it here. If you press, you can find the Tiny Llama -1.1b Q LoRA in here. You can find it here. And then after merging the adapter with the base model, we can use it with the prompt template that we defined earlier. As you can see here, this is the prompt. And then we run the pipeline with the task generation, and the model is merged model. This is the one we ended up with, and with the same tokenizer. And this is the output. The aggregate output shows that the model now closely follows our instructions, which is not possible with the base model.